we had been talking about like geometry review, right? And we had talked about several topics from geometry and kind of re-explain some of those ideas. And today we're going to just kind of continue with that. We're going to do some more like numeric examples. And then we'll do our first Delta Math assignment. The first Delta Math assignment we're going to do in class because I think it'll be helpful for you to have somebody to ask questions to and like, am I formatting this the right way? Or like, how am I reading the directions and making sure that we can be all in the same place to troubleshoot if things come up, right? I'll explain to you how I'll grade this first Delta Math assignment when we get going. But all the problems are going to be based on kind of the stuff that we're going to do examples of right now. So everybody feel good? Okay. Actually, let's put it here. Okay. So let's do a couple of examples. And a couple, I mean like, I don't know, we'll do 5 or 6 or 7, something kind of in that neck of the woods. So we'll look at a couple of different varieties. So let's say we have this triangle ABC, where angle B is 28 degrees. Side AC is X and side AB is 13. And we're asking you guys to solve for X. What mathematical tool would I be using to do this? Bella, do you know? I thought you were getting ready to say something.
Oh, no.
No? Okay. My apologies. You're making a lot of eye contact, and I thought I saw like a hesitant hand coming up. So, it's okay. Now, I started to hear some whispering from the back. Gentlemen, did you guys? Yeah, so we're going to be using SOHCAHTOA. In this case, specifically, sine would be the one of the 3 that we'd want to use. How did you know it was sine? It was a lucky guess?
I don't know how to say it.
You don't know how to say it. Great. So what we do is we start by looking at the angle that we're given. Relative to the angle that we're given, we have opposite and hypotenuse that we either want to know about or we're given information on. Yes, sir. So we'll get there in just a second when we go type it in the calculator. We'll review that too. I'm just going to table that for just 1 second, okay? So what equation can we write now that we've established that we're using sine? So what's the equation that I write now? I write sine of, what do I put inside there? 28. Good. You always have an angle measure on the inside of sine, cosine, or tangent. Equals, and then sine was opposite over hypotenuse. So what was our opposite in this case? X. And the hypotenuse was 13. Okay, so the geometry is now over. All we're doing now is solving this equation for X. So to get the X by itself, what should I do? Multiply both sides by 13. Good. Because multiplying 13 is going to cancel out the dividing by 13. And now it's calculator time. As Ryan was asking, your calculator mode when we're using sine, cosine, or tangent definitely matters. So there's 2 modes that we would be interested in, whether we're using radian or degrees. Which one would I want to use for this particular problem? Degrees. How did I know that? The angle in the problem is measured in degrees, right? So if the angles are in terms of degrees, and they all will be today, we should be in degree mode. Everybody's cool with that? Again, to get to that screen, I press the mode button, which is right next to the blue one. And then I just moved my cursor so that it was on the word that said degree and pressed enter to make sure it was highlighted. Okay, so I'm just going to do 13 times sine 28. So there's my answer. If I wanted my answer rounded to the hundredths, what would I write? 6.10, right? Why did I use the squiggly equal sign there instead of just a regular equal sign? Because it's rounded. That's the approximately equal to. I'm going to do that every time we do rounding to communicate to you in the notes that this was something I typed in my calculator and rounded. I would not be picky about you guys doing it, but that's what I'm going to do because I'm a math teacher and I like to be specific and precise when possible. Everybody's okay with that? And since these are notes, I'm just going to write in that to get to that number, I just used my calculator. What if instead I had asked you to round this to the tenths place? So you just write 6.1, right? Everybody's cool? Okay. Let's do another that's similar to that. That's a 43 if you had trouble reading my chicken scratches. And if you ever do, please speak up. I fully acknowledge that my penmanship is not the greatest penmanship in the entire world, but I try pretty hard. And I'm more than happy to repeat and let you know what anything is, or to go back and write something and make it a little bit clearer. Okay. So what are we going to do for this one? Great. So again, we're using SOHCAHTOA, and tangent is the one that we'd want to use. How did you know tangent? Great. Does everybody agree with that? So remember that opposite, adjacent are always relative to the angle you're working from. Hypotenuse is always hypotenuse. But okay. So we'll start by writing tangent of 43 equals, and the opposite, which was that? 8, and the adjacent then was x. So the geometry part now over, it's algebra time. To get the x by itself, what should I start by doing? I wouldn't want to divide by 8 because that's going to give me a 1 over x and not just an x by itself. Ryan. Yeah, so we'll multiply both sides by x, and that's really helpful because it allows us to get the x out of the denominator of the fraction. So now it's much easier to solve for x by doing that. Is that okay, everybody? So we got the x out of the denominator. What should we do next? Ryan, I think I cut you off. I think you're about ready to say what you wanted to do next. Great, so now we're going to divide both sides by tan 43. Remember, tan 43 is all just one number. If you typed tangent of 43 into your calculator, you just get like a big long kooky decimal. Rather than writing out that big long kooky decimal, we're just going to write it as tan 43 and let the calculator handle it from there. and I'll show you a neat trick on your calculator. So if you press alpha and then the y equals button, this opens up the fraction option. If you pick option 1, that's your normal vertical fraction. So it'll allow you to write in your calculator 8 over tan 43. So it looks exactly like it does on your sheet of paper. Now for this particular problem, you could have used the regular old division symbol and it wouldn't have been an issue. But there will definitely be things in the future that you'd have to be really careful with your parentheses if you don't use this option. So I'm going to use it a lot to just help you guys all make sure you're familiar with this because it's a really helpful calculator option. Okay, so I got some copying down of things to do because I was busy talking there. So x is about, okay, if I wanted that to the hundredths place, oh jeepers, how would I write that to the rounded to the hundredth? $8.58, good. And what about if I wanted it to the 10th? 8.6. We're doing all these rounding questions because this is typically the instructions inside of Delta Math. When you get a decimal answers, they're going to ask you to round it to one or the other. So I'm just making sure that we feel comfortable doing the rounding. I think we are, but that's all. Okay. Well, I think we're on letter C now, right? Okay, let's take a look at this one. Now this is a little bit different than the previous ones, right? What's different about this one from the previous ones? X is the angle rather than a side length. Excellent, good observation. Everybody see that? We're still going to start the same way though. We're still going to use sine, cosine, or tangent. And it's still going to be, to choose which one, it's still going to be based on relative to the angle, what are we given? So the 11 is adjacent, and the 14 is hypotenuse. So what do I need to use? Cosine. So we'd say cosine of x equals adjacent over hypotenuse. Is everybody okay with that? Okay. So to solve for x, which is what we're trying to do here, we got to get rid of that cosine around it. How am I going to do that? I got to cancel that cosine out that's in front of the x. What can I do to both sides that'll get rid of that? Divide is not what we want to do because cosine isn't a number, it's an operation. It'd be like saying, oh, I have square root of x equals 5. To get rid of the square root, I'll just divide by square root symbol. Right? That doesn't, it's not how that would work. What do you guys think? What'd you say?
Maybe like multiply by cosine or something?
Not by cosine, but cosine inverse. So, and technically speaking, what we're doing here is not multiplication, but I'm going to take the cosine inverse of both sides. And as we mentioned, cosine inverse cancels out the cosine. So we're left with x equals cosine inverse of 11 over 14. Okay? So just as a reminder, regular sine, cosine, tangent, take an angle measure and turn it into like a ratio of side lengths. cosine inverse, sine inverse, tan inverse takes a ratio of side lengths and turns it back into an angle measure, right? So to type this into my calculator to get that angle measure back out, notice above the sine, cosine, tangent on your calculator in blue is the sine inverse, cosine inverse, tan inverse. So I'm just going to press the blue second button and then the cosine button. And then I'll type in 11 divided by 14. You could also have used that fraction command I showed you earlier there. But here there's like no parentheses or anything going on. So rounded to the hundredths place, I'd say my answer is 3221 or 3821, excuse me. Yay, yay, yay. Did it again. 38.21. Or to the 10th, we would say it's 38.2. Everybody's cool with that? Okay. Let's see. What if we have let's do 7, 13. Let's say we want let's make that cosine b. Okay. All right, so the question here, you're given this triangle. It's a right triangle where side AC is 7 and BA is 13. And we're asked for the value of cosine B. Okay. So again, we're going to start with looking at where the angle is. So there's angle B. Everybody agree? What is cosine? Adjacent over hypotenuse. So which side is the adjacent side? BC, which we don't know, and the hypotenuse is 13. Okay? So in order to write this ratio of adjacent over hypotenuse, we need to figure out what that adjacent side is. We need to figure out the length for side BC. How can we do that? Well, we have two sides of a right triangle. There should be an obvious tool available that we could use. If you have two of the three sides in a right triangle, what was that? Somebody say that? Yes. Pythagorean theorem. Absolutely. Very good. Thought I heard somebody mumble it in the back. And again, if you think even if it's just kind of a guess, it's okay to guess, right? It helps me. It tells me kind of where your head's at. There's never any penalty for being wrong. I'm never going to be like, wrong, you fail, right? Like, we're not going to do that. You know, this is all review right now. I don't expect you to like have this stone cold memorized. That's why we're doing it again. Okay. And I think a lot of times it helps just like keep you engaged by talking through kind of what you were thinking and, oh, maybe that wasn't the way to go. Look, I was thinking this, but we're doing this, you know, and then it gives me the opportunity to be like, okay, yeah, you could do it that way, but this way would have been easier, or like, no, you can't really do it that way, and this is why, to help so that you don't make that mistake again in the future. You know what I mean? So again, if we're doing this and we're just kind of like asking what to do, and you have any kind of inkling, go ahead, just volunteer, no big deal. All right, great. So we have Pythagorean theorem. What do we have to be careful about when we're plugging the numbers into the Pythagorean theorem? Okay. Specifically, we have to make sure the hypotenuse goes in for C. Very good. So which one was the hypotenuse again? 13. So that's the piece that matters where it goes. Does it matter which one I make A and which one I make B? No. So for the sake of argument, I'm going to call BC X. So I'm going to have x squared plus 7 squared equals 13 squared. Everybody's cool? I do not have one handy. If you need to run to the restroom to get some, did you spill?
Yeah.
Yeah. If you go straight to the right, bathrooms are on your left. You probably know this because you're upperclassmen. I'm used to having to tell the freshmen in community time where to go. Anyways, so to solve for x, I can just subtract 7 squared from both sides, and 13 squared minus 7 squared is 6 squared, right? No. If you're shaking your head in the back, be like, that doesn't make any sense. Yeah, that was a trick. I'm not going to mean trick you, but I'm going to every once in a while suggest things that are maybe common mistakes and see, just to get your attention. What was wrong with what I had said there? Why can't I say 13 squared minus 7 squared is equal to 6 squared? It's a relatively easy reason why you can't do that.
Oh, because it's a square root.
Kind of. I would say the easier explanation would just be that the order of operations says you have to do exponents before addition and subtraction. So to do 13 squared minus 7 squared, we have to do the squaring first before we do the subtracting, right? Everybody's cool? Okay. Again, we're just talking through. And now we can subtract 49 from both sides. Okay. So far, so good? Okay. Now what? Because again, we got to get x, not x squared. Square root. Great. When we square root both sides of an equation, what do we get? A plus or minus. Now, in this case, do we really need the plus or minus? No. Why not?
Because it's the length of the side.
Great, because it's the length of a side. Can the length of a side ever be a negative number? No, that doesn't make a lick of sense. A physical shape can't have negative side length. That's bonkers. So I'm not going to bother with writing the plus or minus. I'm just going to write it as square root 120. Now, here's where I'm going to pause for a second, because depending on the instructions, I'm going to do a couple of different things possibly. Okay? If my instructions say rounded to the whatever, it's just calculator time, right? So I would just do square root 120 divided by 7 into my calculator. So this is one where I'm going to use the fraction command. So I'm going to press alpha y equals, and then take the first option. I'm going to do the square root of 120, and then the denominator I'm going to put a 7. So if I'm rounding to the 100th, I would get 1.56. Or if I'm rounding to the 10th, I'd get like 1.6, right? Now, what if my directions say I want the answer to be exact with reduced radicals? What does that mean? Well, exact means no rounding at all, right? So like 2/3 is exact, but 0.66 is not. Everybody agree with the difference? Okay. So, yes, sir.
So you know how you did the square root of 120/7?
Mm-hmm. Oh, I should have put 13 there.
Okay.
Thank you. Yes. Yeah, thank you. If you catch me making a mistake like that, absolutely speak up. So just as a cool calculator thing, so I just mistyped this, right? If I press second and enter, it'll give me the thing that I just typed into my calculator, and I can just go back and edit what I have. It's a little bit less button pushing, just so you know. So I have 0.84 and then 0.8. Thank you. I appreciate that we're paying such close attention. That's awesome. I won't act like I did it on purpose. It was just a mistake. All right. So exact meant no rounding, so we're just going to write this as a fraction. The reduced radical part, though, is the piece that I really have to worry about. What is a reduced radical mean? Yeah, Ava. Yeah, simplifying the square root down more. So how do I simplify down a square root? Like that. What am I looking for? To reduce a radical, what do I have to simplify that square root down more. Well, to do that, what do I need to look for? So, Luke. Great. So I need to look at factors of 120, the numbers that divide 120 evenly. But even more specific than that, I'm only looking for certain factors of 120. What kind of factors of 120 am I looking for? I want them to be perfect squares. So numbers that you can take the square root of. Okay? So an example of a perfect square would be 36, because the square root of 36 is 6. What's another one? 1, because the square root of 1 is 1. Sure. Anybody else? Nine, because the square root of 9 is 3. Yep. So let's just kind of write down some of these perfect squares. So 1, 4, 9, 16, 25, 36, 49, 64, 81, 100. Those are the first 10 perfect squares. Now 1, if we're reducing radicals, isn't going to help us any, right? Because 1 is a factor of everything. That doesn't... Are any of those perfect squares a factor of 120? 4 is, right? Because I know 3 times 4 is 12. Everybody's cool with that? So we can say that 120 is really 4 times 30. You can always just type in your calculator, right? 120 divided by 4 is, and you just check each one. And hopefully from your Algebra 2 class last year, you remember that you can break a radical at multiplication or division sign. So the square root of 4 times 30 can be the square root of 4 times the square root of 30. And why is that beneficial? Because we know the square root of 4 is 2. Yeah, exactly right. So that is our reduced radical, because I noticed that if I look at 30, none of the other perfect squares are going to divide into 30. Everybody's cool? Other than one, which we don't care about, right? I should be specific. Okay? So when I write my answer with reduced radicals, my adjacent is really going to be 2 square root 30, and the hypotenuse will be 13. Should we do another one like that? That's probably worth doing a second example of, right? There's kind of a lot going on there. It'll be less the second time through. I don't have to like really go through and like intricately explain everything that we're doing again, now that we've seen kind of the process and the reasoning behind what it is that we're doing. As just a little aside while I'm preparing this next example, is the pace going okay? This is appropriate speed for you guys. Not too fast, not too slow. And the level of detail that we're going through on these the first time, it's filling in all the blanks for you guys. Is that okay? Especially early on, I'm going to try very hard to be like especially thorough when we're going through these things, and it might take a little longer than it needs to, but I think that's okay. Especially early on, I want to make sure that we're kind of at a pretty similar place with the things that we remember and we can do. Okay. Okay, so here is the triangle we're given. Side BC is the square root of 47. Side CA is the square root of 41. And we're asked to find the sine of A. So, just like we've done before, we locate angle A. And since we're using sine in this case, we're going to do opposite over hypotenuse. We're missing the hypotenuse, though. To find that, we're going to use the Pythagorean theorem. So doing that, I'm going to say square root of 47 squared plus square root of 41 squared is equal to x squared. Everybody still good? What nice thing do you notice is going to happen here? The squares and square roots just cancel each other out, right? So we just have 47 plus 41 is equal to x squared. We're okay with that idea? 47 plus 41 is 88. And then we'll square root both sides. If we want a rounded answer, that's enough, right? We can just use the square root of 88 if we want a rounded answer. So we'll just write here square root 47 over square root 88. And then just go to our calc. So that gives me 0.73 if I want it to the hundredths. if instead the directions had asked for the exact answer using reduced radicals, I'd have a little bit more to do. Is that, we're so far so good? Henry.
So when asked for reduced radicals, you just give the equation with reduced radicals as the answer, or do you have to still find point?
No decimal. Your answer will be a fraction.
Okay.
Yep. So, square root of 88. Do we notice any perfect square factors of 88? 4 is a perfect square factor of 88. 4 times 22 is 88. And the square root of 4 is 2. So we can write this as square root 47 over 2 square root 22. Everybody's okay here? Now, does this look like the way we'd want to leave our final answer? No. What's wrong with this? There's a square root in the denominator, right? Think along the way we agreed as a mathematics community that we were going to not leave our answers with square roots in the denominator, right? Does that sound familiar? Like something we would have talked about, especially in your geometry class. This comes up quite a bit. Do you remember what you need to do to fix that in a situation like this? Ooh, close.
Very close.
We're just going to multiply the top and bottom by the radical that's in the denominator. Why is that going to fix our problem? Yeah, what you have is in the bottom, then you have the square root of 22 squared. So those would just cancel out. And you'd end up with just 44 then. 2 times 22. Is everybody okay with that? I've left the numerator blank because, quite frankly, I can't type or can't do 47 times 22 in my head at this point in the day. My brain is too cooked. So that's 1,034. So I know 1,034 is reduced. I do, and it is. Let's explain why. Sound good? The easiest place to make that observation is back here. I recognize 47. That's a prime number. You guys know what a prime is? It's a number that can only be divided by 1 in itself. 47 is prime. If I write 22 as a prime factorization, that's 2 times 11. Everybody okay with that? So the only factors of 1,034 are 47, 2, and 11. None of those are squared, right? I don't have 2 2s or 2 11s or 2 47s. There's just one copy of each prime. There's no perfect square in there then. So I would be done at this point. This one was worse than any of them that would end up in seeing in the delta math. I don't think you'd have to do this rationalize the denominator process here. That's what this is called. I think if you had one like this in the delta math, the 88 would have ended up being a perfect square, which is probably what I should have thought a little bit harder at and just made it something that would have worked out. But you know what? Like, messed up, guys. It's okay, right? You forgive me? Today, anyways, right? Tomorrow you may not be so generous, but today it'll be okay. All right. This feels like a good place to stop. We've covered, I think, enough problems to where we should be able to at least be able to start and do things on the delta math piece. And if you still have questions then, that'll be okay. So I'm gonna stop our recording because from now on it's just gonna be you guys doing delta math stuff.